Amazing. Thank you for the introduction. Yeah, so I'm Sydney and this is Gianni, and today we're going to be telling you about our quantum algorithm for reducing induced representations, which is joint work with Patrick Hayden, and which is based on this paper that we put out in October and another one which should be coming out very soon, hopefully. So this work was motivated by a project that we did constructing an efficient quantum algorithm for port-based teleportation. Which I am sure you are all experts now on, thanks to Dimitri's talk. In the process of constructing this algorithm, we discovered a really interesting novel algebraic object, which we are calling a generalized induced representation. So I'm going to remind you about how port-based teleportation works, and then introduce what a generalized introduced representation is. And then my collaborator Gianni will come and tell you about our general algorithm for reducing generalized induced representations into EREPs and applications of this algorithm beyond port-based teleportation. Okay, so port-based teleportation is a variant of quantum teleportation where Alice and Bob share n-1 pairs of quantum systems that we call ports, which begin in a joint entangled resource state. And Alice has an additional nth quantum system in a state which she wishes to teleport to Bob. In order to do this, she performs a POVM on her ports and the system and receives outcome I, which she then classically sends to Bob. Bob then discards all of his ports except for I, which, depending on the choice of POVM and the entangled resource state, will then hold the approximately teleported state. Now, this is a lot of work to do to perform quantum teleportation, and it's a lot of entanglement to use. Why would you do it? The reason is because Bob doesn't have to perform any decoding at the end. Port-based teleportation is, in other words, unitarily equivariant, which means that Bob can perform a unitary operation on the teleported state even before he knows the outcome I. How? Simply by performing the unitary operation on all of the ports. Then he knows that it has certainly been performed on the port I. Okay, so we focus on the port-based teleportation protocol where the entangled resource state is n-1 pairs of maximally entangled qubits, and the POVM is the pretty good measurement to distinguish these states rho I, which are the maximally entangled state between Alice's ith and nth port, and the maximally mixed state on all of the other ports. And these pi I are the measurement operators. For this choice of the resource state, the pretty good measurement is the optimal measurement. However, unfortunately, it's a bit difficult to implement because of the matrix power on the port-based teleportation operator rho. So our strategy to do this is to harness the symmetry of the measurement. So in particular, if you look at the maximally entangled states in the states rho I, you can rewrite these in tensor network notation this way, which is actually equivalent to performing a permutation between the ith and the nth system, followed by a transposition on just the nth system. So we have this written out here as first the permutation between I and n, and then the transposition on the nth system. And so what this means is that the states rho I and the port-based teleportation operator rho are both elements of the algebra of partially transposed permutation operators, which we write this way, which is just, permutation operators that have been followed with a partial transposition on the nth system. So this is connected to the algebras that you saw in Dimitri and Quinn's talks by, this only has a single partial transposition. You can have more partial transpositions. Okay. So it's within the representation theory of this algebra that we discovered generalized induced reps. So now I'm going to back up a little bit and introduce what those are. Okay, so suppose that you have two groups, a group G and a subgroup H, together with representations, a representation rho U of G, and one of H, which is just rho restricted to H, and which is on a representation space V, which is a subspace of U. So a generalized induced representation is going to be a way of lifting the representation V of H to be an interesting representation of G. So it will be some sub-representation of U that's interesting. The way that we do this, we define V lifted to G to be the span of what we get when we act with rho on all elements of V. And this is a really natural thing to do because V is a subspace of U, and we know how rho acts on all of U, so we know how to act with rho on V. And what we get at the end will be a representation of G, and that's what we're calling a generalized induced representation. Notice that when rho acts by an element of H, that will preserve V because V is a representation of H under rho. And so whenever we have a generic group element G, we can break it down into a transversal taken from the quotient group G by H together with an element of H. And so when rho G acts on V, we can first act by rho H on V, which will give us something in V, and then by rho tau. So this becomes rho tau on V prime for some V prime. And what this means is that we can rewrite our generalized induced representation this way, just as a sum over these isomorphic transversal spaces that are each defined by a different transversal rho tau acting on V. Okay, we're calling these generalized induced reps because true induced reps are just a specialized case of what we get here, where this sum over the isomorphic transversal spaces becomes a direct sum. In our formalism, this can happen. One way this can happen is when the representation rho u of G is the regular representation of G, and the representation V of H is a subspace of the regular representation of H, which is of course a subspace of the regular representation of G. Then when rho acts on V, it acts very naturally by group element left multiplication. So we can break any element of V down into a sum over elements of H, and then rho tau will act by simply multiplying every element H by tau. When this happens, action of two different transversals, tau and tau prime, will map V into disjoint subsets, C tau H and C tau prime, and because these subsets are disjoint, they will be linearly independent, and we get this direct sum as above. Okay, so that's what an induced rep and a generalized induced rep are. Back to port-based teleportation and the algebra of partially transposed permutation operators. So it turns out that the algebra of partially transposed permutation operators has some E-reps H alpha, which can be written this way. First, as a permutation Jn-1 acting on these states, which are composed of, in blue, E-rep basis states of Sn-2. So these are Schur basis states labeled for some E-rep alpha, together with maximally entangled states between n-1 and n. So what we have here are transversals in red from Sn-1 mod Sn-2, acting on the E-rep basis for the fixed Sn-2 E-rep alpha. So what we see is that these H alpha are actually generalized induced reps of Sn-1 from Sn-2. So we could rewrite them as the E-rep alpha of Sn-2 lifted to Sn-1. Okay, so because the E-reps H alpha are not just E-reps of the algebra of partially transposed permutation operators, but they're also representations of Sn-1, this means that they can be reduced into E-reps of Sn-1. And this is what that decomposition looks like. The important thing to notice here is that this is a multiplicity-free decomposition, which means that operators that have an Sn-1 symmetry, which includes the port-based teleportation operator rho, will be diagonalized. So putting it all together, this means that if we can transform to an E-rep basis of the algebra, which means decompose into these H alpha, and then further decompose each generalized induced rep H alpha into E-reps of Sn-1, we will diagonalize the port-based teleportation operator rho, and it actually becomes possible to implement port-based teleportation in time polynomial in N and D. So I just want to take this time to shout out the other work presented here today, which also implements the similar transformation. Okay, so now my collaborator Gianni is going to tell you a little bit about how we solve this general decomposition problem for generalized induced reps.
Okay, so as my collaborator Cindy has told us, we are motivated to find an algorithm to reduce the generalized induced representations into E-reps to capture the symmetry of port-based teleportation. And to do this, we found a completely general algorithm. And our problem statement is as follows. Suppose that we have an arbitrary subspace V of the rep space of an arbitrary linear representation rho of G, and which is simultaneously a representation of the subgroup H of G. Then we can generate by it a generalized induced representation. And suppose that we already know an orthonormal basis that decomposes the base rep V into irreps of H, then we want to find an orthonormal basis that decomposes the generalized induced rep into irreps of G. And notice that here I'm imposing the orthonormality condition because with respect to a G invariant inner product, because in such an orthonormal basis, the matrix representations of groups, they will be unitary, and so this will facilitate the implementation. And our method is to apply a change of basis to the spanning vectors rho tau v of a generalized induced rep. So it is algorithmic. And our basis transformation will consist of 2 steps and 3 phases. And we will focus on 3 objects, which are respectively the spanning vectors in the 3rd row, their gram matrices in the 2nd row, which characterize the linearly dependency and non-orthogonality, and the matrix representations of group actions in these vectors in the 1st row. And in this diagram, those 3 objects will be transformed concurrently along the arrows of this diagram. So in the 1st step, we'll just focus on block diagonalizing the matrix forms phi into some fixed unitary irrep forms psi nu. And when we've accomplished this, simultaneously our gram matrix will be block diagonalized as well into with the blocks being in the multiplicity spaces of the irreps. And so this means that in the 2nd step, we'll just focus on the 2nd row of eigendecomposing those Q nu and transform them into the identity matrix, which would imply that we have obtained an orthonormal basis. And this procedure can happen precisely because of the red box here, that those Q nu lies in the multiplicity spaces of the irreps. And this is due to our key observation that for any generalized induced representation, the gram matrix always lies in the commutant of the induced matrix representations. And now let's spell the result out in more detail. So in the 1st step, we'll just block diagonalize the matrix form phi, and it is initially already block diagonalized into the inductions from different irreps alpha in the base rep V, where R labels the multiplicities of alpha in V. And so we will just focus on block diagonalizing the induction from each irrep alpha R in V, and using a unitary change of basis matrix U1 alpha. And we found that U1 alpha is equivalent to an inverse Fourier transform of the subgroup H, followed by a quantum Fourier transform of the group G, and where this quantum Fourier transform of G is actually subgroup reduced down the tower of G to H, which means the psi nu R that appears in the formula it's actually block diagonalized when we are restricting to the subgroup H of G and into irreps of H. And the proof idea is as follows. So we are using the Frobenius reciprocity in terms of the spaces of model homomorphisms. So we found an explicit isomorphism map between those 2 spaces and using some tensor homomorphism adjunction, and show that that map is actually orthogonality preserving. So we've obtained an orthonormal basis of the spaces of inductions from an orthonormal basis of the spaces of restrictions. And for each basis element, it's just a module homomorphism. So that means that it will preserve the group action, and so will the matrix form preserve the group action. So T kappa, where kappa labels the basis elements, is actually a part of the unitary matrix U1 alpha. And by stitching together across different basis elements and across different irreps nu of G in the induction, we can obtain the U1 alpha. The 2nd step is essentially an orthogonalization procedure, and it is in general inefficient. But when we are having some specific representation structure, then that may be efficient. For example, in the examples that I will show as follows, this procedure can be omitted. And with some specific structures, such as the orthogonal compositional structure, the efficiency can be exponentially improved. And by the orthogonal compositional structure, I'm meaning that we are having a subgroup tower from the group G to the subgroup H, and then we can reduce the whole problem of reducing induced reps into each level and into some orthogonal subproblems. And at best, we will find that the inductions in each level and from different irreps, they are just orthogonal to each other. And in that case, the efficiency can be exponentially improved. And this structure, for example, happens in permutational diagram algebras. And so the following examples will be just generalizations of the standard Schur duality. So let me remind you of that. The algebra of the symmetric group and the unitary group acting on the tensor spaces, they maximally centralize each other. So they are commutants of each other. This means that the tensor space can be decomposed into a direct sum of irreps of the product group, where each of them is labeled by a Young diagram lambda. Our first example would just be decomposing this space according to this commutant relation. And we'll decompose the tensor space first into a direct sum of Young modules, where each Young module is a representation of the symmetric group Sn, and is spanned by standard basis elements of the same type. And they can be obtained by applying all possible permutations to a fixed vector v in the Young module. And this in particular means that this is a generalized induced representation. The complexity of our algorithm can be easily characterized. First, notice that a row tau v, they are just standard basis elements, so they are orthonormal. So the multiplicity separation, essentially the orthogonalization, can be omitted. And the unitary matrix U1, we can characterize it by the quantum Fourier transform of Sn subgroup reduced down to the tower of Sn1 times Sn2 times ... Snd. And this is not the standard Schur quantum Fourier transform. This is called the split basis in the mathematics literature. And we've noticed that there was a pre-existing claim in the literature that we can decompose the Young modules by induced representations and hence the Schur transform efficiently in this way. But unfortunately, that algorithm was incorrect. And our second example will just go back to H alpha in port-based teleportation. And this can be easily generalized to K-port-based teleportation by having our H alpha to be a rep space of the K-system transpose permutation algebra. And the complexity of decomposing H alpha can be characterized first by noticing that the grand matrix Q has the same eigenvalue with another different dimensional operator rho that appears in port-based teleportation. And by character theoretic calculations of the eigenvalues of rho, we can obtain indirectly those of Q, and we'll find that it has the general eigenvalues in each block, and hence the orthogonalization can be omitted, because U2 was simply doing nothing on something proportional to the identity. And for U1, it is the standard quantum Fourier transform reduced down the standard tower, so it is efficient. And when k equals to 1, the non-diagonal unitary non-unitary matrix, the diagonal non-unitary matrix D can be incorporated efficiently into the whole circuit for port-based teleportation by adding ancillas and using block encodings and amplitude amplification. And this is the source of the efficiency of our whole circuit for PBT. And finally, let me just expose you to a few more generalized induced reps in diagram algebras. And those are also some generalizations of the standard Schur duality. So in the first row, we have the standard Schur duality between the algebra of the symmetric and the unitary group. with the young modules being some induced representations. In the second row, we have the matrix algebra for the Ward-Bauer algebra, whose commutant is the mixed representation of the unitary group. And in the third and fourth row, we have two types of Bauer algebra, whose commutants are respectively the complex orthogonal group and the complex symplectic group. And we'll be showing in our paper that, in fact, those three, the irreps for the three types of Bauer algebras, they are all generalized induced representations shown in this table. And furthermore, by first decomposing some so-called spaces of harmonic tensors or traceless tensors, we can obtain the generalized induced reps to decompose in the first space place. And that can, in principle, allow us to decompose the tensor spaces into the irreps for the commutants. And that's all. Thank you for listening.
So any questions?
Thank you for a nice talk. I have a question about the possibility of generalization of this result for the multi-port-based teleportation scenario. Have you already tried the generalization for the multi-port teleportation scenario?
Not yet.
Not yet.
Okay.
And do you suspect some, difficulty if we want to generalize this to general?
Yeah, so actually something that is, so our algorithm will use the blocking codings and they are non-unitary in some parts. So that may present some difficulty in efficiently implementing the multi-port-based interpretation.
I see. Thank you very much.
Yeah.
Can you actually comment on the use of blocking codings? Like why does it come up conceptually?
Yeah, so for example, for our generalized algorithm for reducing generalized induced reps into irreps, we first have to obtain some spanning vectors, and they are in general linearly dependent and non-orthogonal. So we'll have to use the blocking codings to transform into the spaces. And also, like for the final step of normalizing them, we also involve some non-unitary procedure.
But could you use maybe like an I-mark dilation of some sort, like what Dmitry was talking about for the port-based teleportation? In our paper, we were also, like, we wanted to implement a POVM, but then we dilated it to an orthogonal measurement. Do you know, is that also possible in your case?
So we have to explore. Yeah, thank you.
Okay, Dmitry, maybe.
Yes, thank you for a very nice talk. I wanted to ask you to comment a bit more about. So you mentioned that there turned out to be an error in this dual kind of way to implement the Schur transform from the symmetric group side.
Mm.
So did you say that it's actually fixable error or not really?
Oh, so actually the error was before in our generalized algorithm, and there is no error in our algorithm for port-based teleportation. And for the generalized algorithm is, so I have shown exactly all what we have now. So it's correct now.
Oh, sorry. What I meant is that you mentioned that there was a way to construct the Schur transform from this permutation modules, from the permutation module side, and I guess you mentioned that the paper which discusses this contains an error, right?
Yes.
The paper by Hari Krovi, if I remember correctly.
Yeah.
But is this error fixable or not? I didn't fully understand.
I think it's not fixable because if we try to fix it, then it will not be efficient.
Okay. Yeah. Thank you.
Thank you.
Yeah, so you said the difficulty in implementing the pretty good measurement for PBT is in taking the square root of rho, right? So can we not use QSVT for that? And so you don't really need to go to the Schur basis, because rho, I guess from what you can prove, the eigenvalues of rho are lower bounded by some polynomial value, right? And rho in itself is also sparse. So if you just block, can you just not block encode row in just a computational basis and do QSVT to take the square root of it?
I do not think so, because the row, it will be diagonal. It will be proportional to identity, and it's a pseudo projector in each irrad block. So if you are in a computational basis, then it's not possible to distinguish those irrad blocks, and you do not know how to scale them to obtain the square root operation.
Oh. Okay, maybe we can discuss later.
Okay.
I don't understand.
Are there any other questions? Okay, if not, let's thank both speakers again.